My name is Trenjinet, and I'd like to present Project 3 for Group 5. Our group members are Angel Hussein, Zhou Shi, and Trenjinet. In this project, we use a naive Bayes and a maximum entropy classifier with various features to provide predictions of genders for English language name. The labeled corpus of names are from the NLTK packages. The project is structured as data preparation, initial feature generation and classifier training, generation of additional features, application of a more complex model, and the final test of the best model on the whole set. And the summary findings are the most important features for the correct assignment of the name are contained in the ending letters, such as in na are very likely to be female. The naive Bayes performs better than the maximum entropy classifier on the selected set of features, so we use the simpler model in the final set. The final accuracy achieved on the test set was 87.6%. So first, we loaded the NLTK package and the names corpus from this package. And then with a general overview, there are 7,944 records in the total. 37% are male names and 63% are the female names. However, there are only 7,579 unique names in the datasets. So before proceeding, we clean the names occurring multiple times as they do not add information but skew the classified results. Okay, and this is the duplicated names all the way down. Drag down. Okay, and then we found that there are some duplicate names appeared that both gender labels assigned to them. It means that the information contained in these names cannot be used to correctly classify gender, so duplicate records will be excluded before modeling. The data is split into three sets. The first set is the holdout set for evaluation of the final model, and the rest of the two sets, one for final model, one for training the model, and one for evaluating iteration of the model. Then we evaluated the naive Bayes classifier. We use different features as inputs and the cross-validated accuracy as an output metric so that we can quickly swap the features generation functions and re-evaluated classifier performance to find the optimum features. As you can see here, the accuracy of the model is 81.3999%. So we see that in this single validation fold, the initial classifier correctly assigned over 75% of the levels, which is significantly better than the using default split into data. So based on the Bayesian likelihood ratios, the last letter seems to be most decisive factor for the male or female label. Using a simple cross-validation approach by iteratively randomly splitting the training data into training and the developed test sets, we can see how stable these results are in terms of the predictions accuracy. Okay. On average, the initial classifier will correctly classify about 80% of the names, and also its performance is between 77% 83% in 30 training iterations. For next, we have taken engineering the additional features. We engineered the additional features and compared the accuracy with the above base model. Adding a two-letter prefix and the suffix features, as we saw that the last letter of the word seems to carry more information, and counted the occurrence of similar sounding consonants based on the soundex group. We can see that on average the approach with added prefix and suffix performs better than the original approach, and it classifies about 84% of the names correctly. So with adding prefix suffix features, we found that the classifier seems to perform better for male names than the original one. The suffix na, la, ia are very strong predictors for female names, as well as as the last letter. So probably largely this is already captured by the last letter feature. And the suffix ed and rt are the important for male names. For the second part of the engineering, we added counts of similar sounding consonants based on the soundex. We see that using the similar sounding consonants does not improve the performance above the original version. We tried expanding the prefix-suffix approach further from the ending of the word to see if additional combinations provide better predictions, or if we will already see worse performance due to overfitting. A significant improvement over the previous versions to around 88% accuracy and a smaller variance in the accuracy. Finally, we can try different classifier algorithms that accounts for possible interactions between the features, a maximum entropy classifier. We use 10 cross-value iterations for maximum entropy classifiers. Here's the cross-validation. We see that this classifier performs on par with the naive Bayes on the same set of features, achieving about 86% accuracy. So then we expect a random training fault to understand the feature importance for this classifier. From the model, we found that the feature importance of the maximum entropy model is significantly harder to interpret, as multiple feature interactions are involved in the defining probability of the level. Second, the errors returned by this classifier show some difficult cases where it is hard to say from the sound of the name to which gender it belongs, such as Rafa or Hollis. However, some simple names such as Emily were also misclassified. And next, as both the naive Bayes and the maximum entropy classifier performs well on the training data, we chose a more parsimonious model, naive Bayes, to continue the test performance on the holdout test set. Here we trained the naive Bayes classifier on the full training dataset. For results, the final performance on the test set, the final naive Bayes classifier is performing comparably well on the holdout set compared to the previous cross-validation iterations, achieving 87.6% accuracy. We can see that among the remaining 62 misclassified males and the female names, a few are rare or unusual sounding for the gender. Thank you for watching the Growth 5 presentation. Thank you.